Topic 5-2, referenced in our Holt textbook, Chapter 5, Section 5, pages 332 through 339. And we'll go over this picture in a minute. What I want you to do first is to ask your teacher for the triangle, I don't really know exactly. I think they call these snap legs, snap tools. But in order to understand how triangles are formed and the values that they can have, this is a helpful activity. So I'm going to give values. I'm going to see if this will work if I just slide this over so that you can see that these are the values and the colors that we're going to give to work with this worksheet. Okay, looking at the very first topic page, we're going to go through these answers side by side so that we can have our values. So take these triangle snap legs, and these are going to be the legs of your triangle. The orange represents the 2, and we're going to take 3 of them and snap them together. So if you've got 3 snap together, I'll put them down here like that. That's actually could make a triangle. So you're going to put a Y or go ahead and spell it out. The classified by its sides, well, all of them are the same color, so all of these would be equilateral. All right, now take 2 2s and 1 3. It's a purple. And snap them together. Okay, was it able to snap? Yes. So it made a triangle. The type of triangle this would be, whether you this way or turn it around, you have 2 of the same color, so that is an isosceles triangle. All right, this time take 2, 3, and 4. An orange, purple, and a green. And snap them together. And once again, you're able to make a triangle. They're all 3 different colors, so that's representative of all different side lengths. Every one of these is different. So yes, it makes a triangle. It's a scaling triangle. All right, now do a 2, 3, and 5. You already have the 2 and 3, the orange and the purple, and a 5 is a blue one. Now, if it doesn't snap, don't force it. But I'm going to lay this down, and if you'll notice, you can't, I mean I could, but it's going to bend it, and we don't want to bend it. I can't snap this together, and we're going to talk about the reasons why this is not a triangle. It could not form a triangle, so the answer is no. There's no classifying its sides. We'll go over some examples of reasons in a minute. Let's keep trying these. A 2, 3, and a 6 is you're going to keep the orange and purple. This time you're going to snap a red one if you can. Don't force it. You're going to notice that just as the 5 didn't work, this one's not going to work either. You can't snap that together. I can stretch and stretch and stretch, and it's still not going to snap without bending one of these legs. So the answer again is no, so it cannot be any type of triangle to classify. Okay, now let's try a 3, 4, and a 5. 3, 4, and 5 is purple, green, and blue. And that one easily snaps together. So yes, that's a triangle. And the type of triangle is scaling. Okay, a 3, 3, and a 6 is purple, purple, and a red. Purple, purple, and a red. What you're going to notice is this one could form if you bent it just a bit. And the reason is, but they'll never meet unless it forms a straight line. So let's look at this one. And we're going to discuss these reasons here in a minute. So a 3, 3, and a 6 is actually two lines. Two of the purples make up the red. They're exactly the same. So it did not create a triangle, it created a straight line. A 3, 3, and 3, of course, we don't need to snap this one together. We know that is going to be an equilateral. They would actually work. A 3, 3, and 4, that one's going to work, and it's an isosceles. A 3, 5, and a 6 are all different sizes. You're welcome to snap those, but for time purposes, we're going to go ahead and I'll let you know that that one actually is 1, 2. All the numbers are different, so it's a scaling. All right, using this information that we filled in the table above, we'll be able to start looking at our inequality triangle theorem that we'll talk about at the bottom. So if you'll notice, all of these numbers are exactly the same as the chart up here. So could a triangle be made or not is actually you're going to be filling in the exact same up at the top. 3 yeses, 2 no's, yes, no, yes, yes, yes. Okay, but we're going to talk about the sums of the shortest sides. If you take the sum of the shortest sides, the two shortest sides for this one, it would be helpful if we did this like that. The sum of the two shortest sides, let's slide this over, is going to be 4, and the larger side is a 3, and you notice that a 4, the sum of the two smaller ones, is greater than the larger side. The two shorter sides are 2 and 3. 5. 5 is greater than 4. 2 and 3 is equal to 5. So the two shorter sides add together are actually equal to the other side. That is the key thing as to why it is not going to make a triangle. The equal sign. I'm going to highlight that. That's an example of like the one that we just did, which showed the red equal to 2 of the purple ones. We'll get to that one in just a minute. Again, this one is 2 and 3, which is 5, and that's actually going to be less than the larger side. 3 and 4 is 7, and 7, of course, is greater than 5. 3 and 3 is 6. Again, we have one that's equal to the larger side. So if it's equal, or we've noticed it's less than, then the answer is no. It's not a triangle if those conditions happen. A 3, 3, and 3, these two added together make 6. 6, of course, is greater than the other side, so that's why they were able to snap together. 3, 3 is 6, and that's greater than 4, the larger side. And, of course, 8 is greater than 6. So what we were able to discover from this, we found out that in order for a triangle to be constructed, make sure you get this word in there, the sum of the smaller sides, so you're going to be adding two sides together, must be greater than the larger side. So you've taken two sides and they always have to be greater than the larger side. This theorem can actually be stated not necessarily sides being the smaller sides like I put on the front card, but if I drew any triangle, if I add 2 of its sides, it has to be greater than the side that we didn't add. So any two sides, if you want to copy these down on your notes, you can. Any two sides added together have to be, the value has to be greater than the third side. And that is the triangle inequality theorem. So, moving on to page, well, they don't actually number these examples. This example, we'll get rid of our triangle snaps. And look at this one. You've got determine whether the sides would make a triangle, and if yes, then classify that by its side. So we're going to first add each one of them. Well, we know that 8 and 9, the two smaller sides, is equal to 17, and 17 is greater than 10. So that would be yes, it does form a triangle. The kind of triangle, because all the side values are different, is a scaling. Notice the two smaller sides would be the 1 and 1. 1 plus 1 is equal to 2. So if you add these two together, you're getting 2 that would be equal. So that would not create a triangle, therefore cannot be classified. 6 and 6 is 12. 12 is greater than 10. Maybe we should write that. 2 is equal to 2. That's why that doesn't work. 17 is greater than 10. If you want to make some notes here, you can. So that does create a triangle. 2 6's being the same makes it an isosceles. 3 and 5 added together is 8. 8 is greater than 7. So it definitely can form a triangle. And again, all the values are different, so this would be scaling. And of course, 4, 4, and 4 is an equilateral. Okay, moving on. In a triangle theorem, the largest side is opposite the largest angle, and the smallest side is opposite the smallest angle. So if these angles are given to you, this one being 120 degrees, B they're saying is 40 degrees, and C is 20 degrees. When you're looking at the sides opposite these, the greatest one is across that way, and they say opposite. The smallest angle is 20, so you come all the way over here and think of this segment opposite. So drawing arrows on your triangles might help. The largest side is going to be BC, or you could also name that segment CB. And then the smallest side is opposite the 20 degrees, which would be BA or AB. Alright, another theorem states this is dealing with angles, this one's dealing with side measures. So it's also true that when you classify a triangle by its sides, then you're going from the smallest to the largest, the same thing's going to be true. Across from the smallest side length would be B, and they said label them from smallest to the largest. The next largest side is 12, so angle C is going to be the next biggest, and the largest number is 15, so the angle opposite that segment that measures 15 is angle A. Notice all of these have a different value, 9, 12, and 15, therefore it's a scaling triangle. Okay, one last example. If you were to list the sides of ABC in order from the longest to the shortest, if the angles are indicated by these different measures, well, we know that we add up all of these. I could draw this if I needed to, but if you were going to look at a triangle with all these sides, ABC values, you could label them A, B, and C, with A being 10x this one being 5x minus 17, and this one here being 7x minus 1. This is the whole measurement for the degrees, and everything has to equal 180 degrees. So how many x values do we have? Add them up. 10, 7, and 5. That would be 22x. We have a negative 17 and negative 1. That's minus 18. So all of those added together equals 180. Something to remember. You're going to add 18 to both sides so that this goes away. 2x would be equal to, I'm sorry, I don't know why I said 2. This is a 22. 22x is equal to 198. Divide by 22 on both sides, and x is going to be equal to 9. You're not really through here because you have to remember to plug this 9 back in to each of my x's. If you need to, make note by arrows if you want, like I did, to show that you're having to plug it back in. 5 times 9, 45. 45 minus 17 is 33 degrees. 7 times 9, 63. 63 minus 1 would be 62 degrees. And of course 10 times 9, this would, A would be my 90 degrees. So with this being 90, this being 62, and this being 33, the side that's going to, they want us to list it from the longest. So the biggest value is this 10x, which ended up being 90. So the longest side is going to be BC. Come back up here and write it. BC is the longest. The next one's going to be AB, because AB, I'll show it right here, AB is across from 62. If you want to draw it, well, I've got enough arrows growing everywhere. I'll just label them. Just study it closely after you've copied it down. And then, of course, the last one would be AC, and AC is across from 33. And notice that my drawing is definitely not to scale because that actually looks like the biggest side. So just because I threw an example down as a drawing, it's not necessarily drawn to scale because this angle is the smallest and this one was actually the biggest. And if it's a 90-degree angle, I should have made it straight up and down a right angle. But at the time, I just had expressions and didn't know the values. Okay, if you have any more questions, ask to do a couple more examples with the manipulatives. And that is 5-2.